Welcome to the Gardien Podcast Series. The Gardien Group, providing extraordinary solutions to today's exceptional problems.
Hello, Todd Kolmodin from the Gardien Group, welcoming you to another in our podcast series. Today we're going to be talking about an IPC specification, which is called 9252, or the electrical testing of unpopulated printed wiring boards. Along with me today again is Rick Meraw from Toronto, Canada. Hello, Rick.
Thank you, Todd. It's an exciting topic for me today to talk about IPC 9252. A lot of people have many questions, so sharing the information that we know with all is very important. Once again, it's a pleasure being here.
All right, glad to have you aboard, and you'll be throwing down some knowledge to our listeners as well. So what is IPC 9252? Well, IPC is a group that is involved in writing specifications guiding the manufacturing of printed circuits. That could be rigid boards, flex boards, or a combination thereof. But what IPC 9252 is the recent broken out specification specifically for electrical tests. Now, historically, there was another IPC, which they called IPC ET652, which people that have been in the industry for a long time will know what that one was. There's also a TM650, which is the test methodology specification. But what we did after a certain amount of time is we broke out away from the standard specification, which is usually IPC 6012, which is the main specification for rigid unpopulated boards, and we made IPC 9252. So myself and Rick are on the committee that regulates and keeps this document up to date. So from that's where the IPC 9252 came from. We have three different things that are involved in IPC. They have what they call their performance class. When you see somebody send a procurement document or what have you that says we're going to build this to either class 1, class 2, or class 3, that would be the performance class. And table 4.1 in this document, and if any of you do have the document, you can search a few pages in and it'll come up. This is pretty much the heart of the specification, is this table. From that, we also, you might hear, there is a test level now in the newer version of the 9252. We have test level A, B, and C, which do correspond to the performance class 1, 2, and 3. So the first thing we need to talk about with the IPC, we talk about in the world AI or intelligence and things like that. Well, we have what we call net list testing, and I think Rick will take us through a little journey on what is a net list and what does that really mean in the world of electrical tests. So welcome aboard, Rick, and take it away.
Yes, Todd, you said it all in that explanation there. But one thing that we can't forget, Todd, in this IPC 9252 is it corresponds with all the other classifications that are associated with the builds, like 31032, the flex specifications. They all come into play, and they all tie into the 9252 when it pertains to electrical test. Now, what is a net list? I don't know if many people watched our first podcast, but we explained what a net list is and what electrical test is. And a net list is a connection between a couple surface mount pads or some holes or via holes in a printed wiring board or PCB. So a net list could have one node. A net list could be a single point net. So you have one pad, surface mount pad, usually in a surface mount package or a quad pack or a BGA, where you have just a pad there to solder to. That would be a single point net. Also, when you have multiple connections, you're going to have a current flow from point A to point B. So if you have a trace that just across from point A to point B going across the circuit board, that is an electrical test net. Now, what's interesting with these nets is when you make these nets, the designers, they have a schematic diagram, and then they use layout software and they lay it out to the PCB. IPC specifies how you can assign the test points, because we know that they put some sort of solder resist on the outer edges of the board and a surface finish on the copper to keep it from contaminating. So in some of these classifications that there are test levels, as Todd mentioned, test level A, for example, we would remove some of the points in the middle of the net, and they would be more of a straight through point. So if you had a line across your PCB where you had a point A on the left edge, point C on the right edge, and point B in the middle, current can flow from A to C without any interference from point B in the middle. Current can flow from A to B. Current can flow from B to C. Now, because current can flow from A to C, and it's straight through, whether it's there or not, you're still going to have a connection to A to C, and you all still have a connection A to B or B to C. We don't need that middle B point. You can save a little bit of, mostly this was done in the past for fixturing to reduce some of the test points when we build a fixture. So you remove point B. That's called a midpoint. Now, that has to be just that, in the middle of a net. It can't be on the end. A would be an endpoint, and C would be an endpoint, because after C, there's no other point. Or before A, there's no other point. So technically speaking, if you had a 3-point net, one trace going straight through it all the way, you would have to be able, you could remove for a couple of the test levels, I think it's A and B, you can remove the midpoint. So you would never need to put a test point on point number B. Now, most people, if the pad was missing, if whatever process, a mechanical process, scraped away the pad and the trace was still there, you would still have a connection. There wouldn't be a problem. But when they went to go solder the components on, or we went to final QC or QA and you saw that missing pad, it would be a defect. But electrically, the board still would work. Now that we know what a test point is, we talk a little bit about a net list. So a net list is a connection of all the nets together. So we have a series of these traces running from one point to another point. Each point that are connected together are classified as one net. So a PCB may have many nets in many different layers across many different layers where you have your points. So you end up with a list of how many nets, how many points. So if I have 3 nets on a board, for example, the first net has 5 points, the next net has 2 points, and the last net has 10 points. I would have 3 nets, 1 net of 5, 1 net of 2, and 1 net of 10.
Very good, Rick. That's a good explanation of netlist and how we do some optimization. One of the things that we have 2 different modes of tests, which we call fixture testing, and then we also talk about flying probe testing. The one thing historically with a fixture test, you're using a full parametric test where all of your nets, as Rick just explained, are tested at the same time, and net 1 is tested against net 2 and net 3 and net 4 and so on, and all of these are tested at the same time. In a fixture test, the full parametric test, if the distance between net 1 and net 2 is 1 inch or 3 inches or 5 inches, it's still tested in the isolations or shorts algorithm to net 1. So The difference with that and flying probe tests is where we talk about a term called adjacency, which is net to net spacing. And Rick will probably provide a very nice explanation of what we mean by adjacency. Go ahead, Rick.
Thank you, Todd. The adjacency, there's a couple different types of adjacency, but if you had, let's take 3 parallel traces running beside each other, so let's call vertically up and down, and you labeled them A, B, and C. We know that there could be a short across A and B, sure, and there could be a short across A and C. But we also know that if there's a short from A, B, C, that all 3 of those traces are shorted together. We would have to test B to C, A to B, and A to C. So that's basically 3 tests. We can reduce that number by doing, as Todd mentioned, adjacency, where we could test A to B. If there's a short from A to B, it would detect it. And if there was a short between B and C, it would detect it. So the short technically from A to C is still there, but it's just using B as kind of the midpoint. So in order to, it's all production time, machine time, it's a little bit of saving. So we do a little bit of a little trick. So we use something called line of sight adjacency. That means that if you see a trace within a certain value, you're going to test it. If you don't see a trace in that certain value, you're not going to test it for a short. So if A and B traces are spaced more than that window apart, so let's say we use, I think industry standard is 50,000.
50 mil, yeah.
Yeah. If we were to test A and B and it was 50 mil, exactly 50 mil, you would detect a short, and there was a short there, you would detect it. But if A and B were spaced 60 mil apart, A wouldn't look for a short against B trace. So you would miss the short. If there was a short there, you would miss it on a flying probe. On a fixture, you would catch it because it's a full parametric test. So as long as the traces are within that window size, you're going to test it for a short. Now, if the traces are closer together and you actually have 3 traces in that window size of A, B, and C, you're going to get that additional test that I mentioned. But because you can't see, vertically see, or horizontally see, this is horizontal in this case, horizontally see the trace. So A to B would be tested, but not A to C. B to C would be tested, but not C to A. Because we want to keep it straight. We want to save a little time, but we want to capture as much as possible that's within the line of sight window. If it's outside the window, we will miss a short. It can happen, it does happen, but it's very seldom. The other thing that's with adjacency is we're talking horizontal adjacency right now, but actually there's something else called vertical adjacency, and that goes from layer to layer. Many of the nets on a PCB board are intertwined together, and most of them are tested. If you have a large net, like a voltage net or a ground net, that's going to be tested against many, many, many other nets in the PCB. But if you have a signal layer and it goes through 2 or 3 layers, and there's another trace that runs above it on the layer above. So if you have a trace on 12 that's running one direction and a trace on 11 that's running another direction, technically they wouldn't be checked for a short unless you turned on something called vertical short, where it goes, basically it's looking at Z. So it's looking through the board itself, same window size. It takes into account material types and different things, but you're going to look for a short in between layer 12 and layer 11 if they're within that window size again. If there's a short there, it'll detect it. So it's a little bit hard to understand, Todd, but I hope that there's a little bit of explanation there. If anybody needs further assistance, I know that we have some additional documents that we can send out on adjacency. And I also know that the modern tips, they've enhanced it a little bit more than the simple explanation, but we try to keep it a little bit simplified. So Todd, what if, I know that we're doing continuity on a circuit board and we're doing isolation check. So what values do we use for continuity tests and what values do we use for a short check?
Okay, that's kind of going back to the table 4.1 in the specification. And just to go back to Rick's explanation on adjacency, the whole adjacency idea is all working with detecting shorts. The adjacency window doesn't mean anything when it comes to continuity. Continuity is the connection between point to point. So in each performance class or test level, we have different recommended parameters by the group for each level. So we talk about voltage, then we talk about isolation threshold, and we talk about continuity thresholds. So we don't see a lot of it anymore, but for a class 1 board or test level A, resistive continuity testing, when we test that board, we want to make sure that we are less than or equal to 100 ohms from point to point. I know that sounds a little bit weird nowadays, but we do have some legacy type product out there that this may be something that is okay to have that kind of value. Resistive isolation testing, again, this is the shorts check. They're asking that we need to have an isolation from net to net between or greater than or equal to 500 ohms. Again, that might sound a little archaic today, but can we do indirect testing or adjacency for isolation, or require the testing of the midpoints as Rick talked about before? In table 4.1, we can use the indirect isolation testing, we can use adjacency, and we can use the optimization method. So every single test point doesn't have to be tested. When we get into class B or class 2 or test level B and C, things get a little bit tighter. With class 2 board or test level B, that continuity threshold now needs to be 50 ohms or less. So any point to point on the board has to have a value of 50 ohms or less. Again, that seems to be a little loose for today's standards. We know that most of us test a lot tighter than that. Our isolation threshold needs to be greater than or equal to 2 mega ohms or million ohms. And we can still use indirect testing. We can use adjacency for isolation when it comes to the probers. And we can also still optimize out our midpoints so that we can reduce cost if it's a fixture and increase some time or increase some speed on the flying probe. Now with class 3 or test level C, this is the high performance product that we see a lot today, where it gets a little bit more tricky. So with resistive continuity testing, we're down to that 10 ohms or less number from point to point on the board. And then we want to be on our isolation test greater than or equal to 10 mega ohm or 10 million ohms. And now when we get into the isolation test using signature comparison, which is the adjacency and capacitive gather, this gets into what we call an acceptability between the customer and the supply, or the supplier and customer, or in our term, they used AABUS, as agreed between user and supplier. So if on a class 3 product or test level C, if you wanted to do flying probe, technically we need to have a conversation or a document in a paragraph in the procurement document or something that allows the flying probe test using signature comparison and adjacency. Well, mostly signature comparison. If you're going to do a standard full resistive test for opens and shorts on the flying probe, it can still be done on the flying probes. But if you're going to use the indirect isolation or indirect testing by signature comparison, as it's called, then you need to have an agreement between the user and the supplier. It just is not okay to just do that. What we also get into here, we start getting into a barrier on the requiring testing of the midpoints. With test level C, on the class 3 product, this is a required test of the midpoints. And the reason for this is, as Rick mentioned earlier, reliability of high performance product. They don't want to have a problem at assembly or in the field. So if you had a point to point, 3 points on the net, the center point was originally on class 1 or 2, optimized out, but they had a problem with solder mask and they solder masked over that pad, but a component's going to go there. With a class 3 or test level C test, you're going to identify that pad being covered by solder mask and it will stop. So in a nutshell, that's a lot of what the table is all about on requiring voltage parameters. There is one thing I need to mention though. We run into this, I'm sure Rick can agree, that when we're testing, we have some high performance product, and a lot of times this is on bigger layer boards, multi-layer, high surface square foot on the board, where we have a trace that might be extremely long. A lot of times these can be referred to as timing traces. Sometimes people call them heater traces or something like that, where the point to point, end to end is very long. And IPC uses a referee number for distance and value of ohms as basically being a half an ohm per 25 millimeters, which is about 9.984 inches or so. So when you get extremely long traces and you're trying to test at test level B, where we want 50 ohms, but most of us use what today is 20 ohms or less, and class 3 product, test level C, 10 ohms or less. And if you have a real long trace, you might have that one trace in the board coming in at 17 and a half ohms or 20 ohms. And the rest of the board passes, but you just can't get this one to pass. Well, this referee allows us to go back to our vendor or the supplier, or you might have to go all the way back to the engineering group and say, hey, this net is exhibiting 17 ohms. We can't get it to pass at 10. But based on the referee number for copper, we can see that the number that we're getting for this length of trace is actually within specification and can still be allowed to pass. So that's breaking down table 4.1. If you have anything to add to that, Rick, I know I got kind of long-winded there.
No, it's a very good explanation, Todd. I know that this is the heart. There's a lot of information on this table, and I've referred to this table many times already, going back and forth on various activities.
Okay.
But how does this table play with like military and aerospace, Todd?
Okay. That was going to be our final last topic of discussion. So we have class 1, 2, and 3, test level A, B, and C, and this corresponds, like Rick mentioned, a lot of specifications out there, IPC 6012, 6013, and Rick also mentioned some of the military, 31032, 5884, 55110. You go look in those and you just find the ET in there, and it always says go to 9252. But there is a difference with 6012. You'll notice if you're the procurement person for those documents, there's also what's called a 6012 DS, or also there's a 9252 DS, which is used to be in the original specification 6012, there was an appendix, and it would say exceptions for military and space avionics. And so they broke that down into another specification, which they call the DS, which basically is the same thing as far as test goes, with the exception of some parameters. With test level C, or class 3, we call that, there's an exception, they'll call it 3A or test level C/A, which means it needs that addendum or extra test. So the difference there is our voltage. We didn't get into voltage really earlier on in this, but for most printed wiring boards to be acceptable by the military, for one, it needs to be a 40 volt minimum test. And there'll be a statement sometimes in a procurement document, or usually in a fab drawing, it says that this board, the rated voltage is X. Sometimes it'll be 10 volts, 12 volts, 18 volts. And when you see a statement like that where it says the maximum rated voltage of this PCB is 12 volts. Must remember that that is a statement. That is not telling you what to test the board as. They're telling you in the duty cycle of this board that the maximum rated voltage that it will see will be like 12 volts. Now, if they say that you will test, you want to look for something where they're telling you to test. If they say test voltage shall be 12 volts, okay, then you're wrapped into that and you have to test at 12 volts. But you might want to check with your customer if they make a requirement like that, because military guys, they are wanting that 40 volt minimum to be acceptable under those military specifications. But anyway, long story short, back to the space and military avionics exception. That has to be a minimum of 250 volts. This can't be 100 volts. It can't be 50 volts. We need to have 250 volts minimum. And then we also, when we get into that isolation threshold, which we were class 3 or test level C, was 10 megohms or higher. For this classification, we need to be at 100 meg or higher. And that's the big difference. And also there will be usually no allowance for flying probe test, but whether it be adjacency, indirect signature comparison, or direct full resistance. For the military and space avionics exception, they usually are pushing for the full parametric test, which requires a fixture tester. There is some exceptions to the rule. There always is. You always need to consult your procurement document or your fab drawing or specification. And when in doubt, definitely go back to your customer, because these are the really high reliability products, and we want to make sure we test them specifically what the engineer was intending. Do you have any further comments on that, Rick?
And that was a very well put, Todd. Exactly what you said. I know that with the 6012 product, aerospace product mill, there is some special requirements, and you got to read the drawings, the fabrication drawings properly. I've seen in the past sometimes that we do test, or somebody's tested them wrong and they have to be retested, so it creates multiple work. It takes longer to do, and maybe a RMA at the same time. The fabrication drawing says it all, and the specification says it, confirms it, but we need to make sure that everyone who's ever doing it, you shouldn't take any side steps on it. It's in black and white. It should be followed to the T in order to certify that product is correct or not. But other than that, Todd, I think that was a great explanation. Thank you for that, Todd.
Thanks, Rick. And you know, one thing I when I was talking about that, we want to, you know, specify or really, you know, work on making sure you read the fab drawing, find those notes in there. And if it doesn't look right to you, definitely question it, because some of these drawings for some of this product has been around for a long time, and they've spun the revs a few times. And an engineer back in 1982 might have wrote some notes in there, and he retired, and then they spun the product, and they just start cutting and pasting notes from revision to revision. And sometimes, like I've done and talked about in quality talks that we've done, that you need to assign these kind of projects to a department and not a person, so that you can keep revision control correct. And what happens is some of these notes are so old that they really don't make any sense today. And so even though some of these notes have been written a lot of times by really smart people, sometimes the requirements can be dumb now, and especially like if they're written a long time ago. So if there is a question on them, definitely take it back to, you know, if you're the person doing the test and you don't understand it, talk to your supervisor. And if there is a real problem, you know, it doesn't hurt to go all the way back to the customer and talk to someone there that says, you know, yeah, you're right, we're doing this wrong. But anyway, that's just kind of a little help tidbit for you guys. And with that, I think we're done. We've kept you long enough for a day. Thank you for joining us. On behalf of Rick Meraw and myself, thank you for joining the podcast, and you can get these wherever you get your normal podcasts. And we'll see you at another one coming up real soon. So wherever you may be, have a great afternoon. And if you need to get a hold of us, drop a line to info@gardien.com. That's info@gardien.com. Have a great day from Rick and myself.